Right now we're going to work on systems of nonlinear equations. When a section of a unit or a class is saying that you're solving nonlinear equations, it doesn't mean you can't include linear. It really just means not exclusive to linear equations. So over here we have xy equals 20, which is not a linear equation, but we also have x plus y equals -9, which is a linear equation. So this first one over here you should be able to recognize as a rational function or the reciprocal function, and this right here is a linear. You can just go ahead and graph them if you wanted, but we're going to solve by substitution first. So what I'm going to do is I'm going to solve for y over here. Really, you have so many different ways you can do this. So y is equal to -x minus 9, and now I'm going to substitute that into this other equation. So that leaves me with the x times y equals 20, and I'm filling in -x minus 9 right over here. What does that get for me next? So from here, if I distribute, I get -x squared minus 9x is 20. This is a polynomial equation. When you solve a polynomial, you solve it by getting it equal to 0 and factoring and setting each factor equal to 0, each hopefully linear factor equal to 0, and using the zero product property. I'm going to get 0 on the left side, so I have all positive leading term. So it's x squared plus 9x plus 20, and that fortunately will solve very nicely for us because it factors very nicely, x plus 4 and x plus 5. We're getting two different answers, so this gives us, using zero product property, we get that x is equal to -4. This first power is significant. The first power, as I solve, tells me that when these two things intersect one another, they are not going to kiss each other or bounce off of each other. Instead, they're going to cut through one another. And the same idea over here. This is x plus 5, set equal to 0, gives me -5. So at x equals -4, they will cross through each other, and at x equals -5, they will cross through each other. However, when you're solving a system, your answer should be an ordered pair. So what we're going to do is we're going to take these x values, fill them in over here to get our y values. So we're going to evaluate this. Now I'm going to use slightly different notation. I know it's not really a function, but I'm going to say the y of. Normally it's y of x or f of x. So I'm going to write the y of -4. The y of -4 is going to equal negative times negative, so 4 minus 9, -5, which means the ordered pair I'm dealing with is -4, comma, -5. And then I'm going to do y of -5. -5 is 5 minus 9, -4. So the other ordered pair, oh, I don't know why I wrote this that way. That's silly. That's y of, and I wrote y equals. Forgive me. So that right there, y of -5, is just saying like f of x. What am I filling in so I can keep track a little bit better? So y of -5 equals -4. So the ordered pair is -5, comma, -4. So both ordered pairs that I'll get are going to be in quadrant 3. I like to pay attention to where they are because then when I go to draw my graph, I want to make sure I do leave enough room for them. So this right here, a little bit separate work, just going to draw some lines over here. If you just leave these random equations like x equals -4, x equals -5, and y equals this, y equals that, well, you didn't really solve the system, okay? The whole point, point of solving a system is finding the points where they intersect each other, and our bonus is that these two functions or graphs, they're going to cut through one another, really intersect. So if one equation looked like this and the other equation looked like that, well, that's what they would look like, okay? That's what a cut through will look like. However, if they were to the second power or the fourth power, instead of them intersecting in that kind of a way, they would more kiss one another or bounce off one another. So it might look something like this. You even learned about that when you were graphing polynomials, and that same is true about how two graphs intersect each other. Now I'm going to go ahead and I'm going to graph. So using the same colors I just saw, I'm just going to rewrite my equations a bit. So the two equations I am dealing with are y equals -x minus 9, and I think this was the color order I did, y equals 20 over x. The linear function is pretty simple. Here's my -9 and my slope is -1. That would mean down 1 over 1, or I could even go say up 4 and over 4 this way, right? I can go up 2 and over 2 that way. I could go up 3 and over 3. I also could have figured out that my x-intercept was going to be -9, so I do have that information to work with, and I'm just adaptable to that, so it looks pretty good. So that right there is the linear equations. Oh, I said I knew they were going to intersect in quadrant 3. That's also why I kind of wrote out some work over there, because I knew it wouldn't really be in the way. Now 20 over x is going to be a rational function. It's going to have a vertical asymptote here at 0 because it's undefined when x equals 0. You cannot have any graph over there. Absolutely not. It is an infinite discontinuity, and my end behavior as x approaches infinity is approaching 0. So here I'm going to have my end behavior approach 0 on this end, and as we approach negative infinity, I'm also going to be approaching 0. So I don't care so much about it in the middle as much as I care about it on the ends right there. Now if I want to fill in some points, a couple ways you could go about doing it. Usually what I do is I know it passes through the points because the parent function is y equals 1 over x. So usually it passes through 1, 1, and negative 1, negative 1. 20 is a vertical stretch, so I'll go over 1 and up 20, and I'll go over 1 and down 20 instead and use those. But that's a little silly because it's very, very big. So what could I do if I plug in 2? I get 10. I don't want to plug in 3, it doesn't go even, but if I plug in 4, I'll get 5. So here's 4, comma 5. If I plug in 5, I'll get 4. And if I plug in 10, I'll get 2. So this right here is going to be one branch. Oops, not my best drawing right here. I know the equation's in the way right now, but that's not the one I'm so concerned with. It's really over here. So same idea. If I plug in negative 2, I'm going to get negative 10. If I plug in negative 4, I'm going to get negative 5. There it is. If I plug in negative 5, did I do that correctly? Negative 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. If I plug, oh, yeah, no, I'm fine. What's this one right here? Negative 5, negative 4. I, for some reason, thought that was supposed to be the negative 5. Sorry. And 10 right there. Okay. So I know they cut through each other. I know this has to be pointing down. Sometimes you're not going to have that much skill and knowledge about the equation, but I know it has to be pointing down. It's approaching that asymptote over there. So I know it's moving along like that. Okay. Now here I'm going to go toward this point. I cut through my green graph, and there I am again, cutting back through it and coming back over to this guy over there. All right. I know it's a little ugly, but that is what it is doing. Okay. Probably be a little bit smoother. So just do your best. But using information like the multiplicity of the factor to figure out how the graphs intersect each other, not just that they do intersect each other, will be really, really helpful in calculus. And when you're in calculus, you're also going to spend some time focusing on finding the area set up between two graphs. So you're going to want to be really good at that. Okay? All right, here we have another system of nonlinear equations. And the first equation here is x minus 1 quantity squared plus y plus 1 quantity squared equals 4. 4 is also 2 squared. And the other equation is y squared plus 2y minus x minus 2 is 0. When I first look at this equation, I immediately know that this is going to be a circle. This is a circle with its center at the point 1, negative 1, and it has a radius of 2, not 4, because that's 2 squared right there. Over here, you have your standard form of a circle. It may vary from book to book. The book and curriculum I use, we see that this is standard form. General form would be if it were all expanded. So your center is at HK. All right, the formula defaults to negative signs in there, so a minus 1 is actually to the right one, and the radius is equal to the r, the number being squared. So if you learned conic sections, if you've learned circles, you should know that that's a circle equation. This, however, is actually a parabola, but this parabola has y being squared instead of x. Since y is being squared, this is a parabola opening in the horizontal direction. It has an axis of symmetry that runs horizontal. So how can you describe this formula, this vertex form? It would look a little bit like this. Y minus k squared equals, you'll have x minus h on the other side of the equal sign. Now it's going to depend on how we look at things here. You might look at it as being an a over here, or a 4p, or 4c, or for something else over here. Okay, I guess for right now I'm going to call that A, instead of using where we would find the focus point in the directrix. So if you learned parabolas that way, you might think of it that way, but I'm going to prefer this form for right now. And in this parabola, the vertex is still going to be at the point HK. And then our axis of symmetry is, like I said, usually what we learn in algebra in the beginning when we learn functions is that we have a vertical axis of symmetry. It's x equals something. In this case, it's going to be y equals something. It's going to be horizontal, and it's going to run through our vertex. So y equals k is pretty good for our axis of symmetry. We don't really need it, but it might help some people in case they forgot a few things. Now, I'm going to start off by solving this system algebraically, and then I'm going to take it from there. I'm going to graph it so that we can kind of see that our work will correspond. You know, our work solving by substitution or elimination will match the answers we get when we graph it. So if I want to solve by substitution, I feel that it might be easiest if I could solve for x, get x alone, and fill it in over here. Or I could, if we look carefully here, if I complete the square on this, like I mentioned over here, if I complete the square, y squared plus 2y, you're going to get y squared plus 2y plus 1, and you'd have 1 to both sides, and you'd end up with y plus 1 quantity squared, which is what we have here. So I kind of feel inclined to do that. So I'll have y squared plus 2y plus 1, and on this side I'm going to bring over the x positive and brought over the 2, and if I add a 1 to one side, got to add a 1 to the other side. Here it's a completed square, so now you could easily factor this. So I have a y plus 1 squared, and that's going to be equal to an x plus 3. So y plus 1 squared equals x plus 3, and up here that's exactly what I have. I have a y plus 1 squared, right? So you don't have to do it this way. It's just an idea. It's something I noticed. So I'm going to go ahead and fill that in. I'm going to expand this. So I'm going to get x squared minus 2x plus 1, and then instead of y plus 1 squared, I'm going to swap that out. I'm going to substitute in the x plus 3 for the y plus 1 squared, and then I have equals 4. Now, what kind of equation am I dealing with? I'm dealing with a polynomial. It happens to be quadratic. I'm going to get it equal to 0, like I mentioned in the last example. X squared minus x, and that's 4, but I subtract 4, so really I'm at this spot where it equals 0. I can solve still by factoring and using the zero product property. I have x to the first power. It's telling me cut, okay? It's cutting through. It's not kissing or bouncing off. I get x equals 0, and I set x minus 1 equal to 0, and I get x equals 1. Those are my two x values. Now, let's find the y values that correspond to it. Now, this is where it gets a little interesting. I'm noticing I have y squared in both equations, so I'm going to start off with, really doesn't matter which one we use. I don't know, I guess I'll use this one. Right over here. So if I'm solving with this one, I'm going to have y plus 1 squared equals something plus 3. I'm going to start off by plugging in the 0. Well, 0 plus 3 is just 3. And I have y plus 1 squared right there. I need to solve for y, so I'm going to take the square root of both sides. When you take a square root yourself, you have to account for all possibilities, so I'm going to put a plus minus out in front. And that gets me to the spot where I have y plus 1 equals the positive and negative square root of 3. And I'm going to subtract 1 over, and I'm going to write it out front, because if I put it on the end, I feel like people mess up. Negative 1 plus minus the square root of 3 is my y value. Now that y value is actually two separate y values. So if I wanted to write some ordered pairs, I'm actually going to get two ordered pairs from this. I'm going to get, so this is using the x equals 0, so I'll write that above there, and that led to that conclusion right over there. So that gives me 0 comma negative 1 plus square root 3, and it gives me 0 comma negative 1 minus square root of 3. Keep in mind, if it's 0 comma anything, it's going to be on my y-axis. So just to kind of help me out before I graph it, keep it in mind, have a vision of what's going on. And what else? We could plug in a 1. If I plug in the 1, I'm just going to, I want to save, yeah, I could write answers there, so I'm just going to go over here. If I go ahead and use the same setup, I'm going to use the x equals 1 this time, so I'll write that over here in a second. Fill in the 1, so I'll have y plus 1 squared equals x plus 3. So I fill in the x equals 1, and 1's right there. Okay, so what does that get me? Y plus 1 squared, which I'm about to take the square root of, is equal to 4. Putting the square root on both sides, taking that, and that's going to leave us with what? We'll have a y plus 1 equals plus minus 2. Alright, from there, again, I have two different answers. I have negative 1 plus 2 and negative 1 minus 2. So I'm going from this x value to these two y values. Okay, so what are these other 2 points? I'll have 1 comma, what's negative 1 plus 2? 1. And 1 comma negative 1 minus 2. So it's 1 comma negative 3. So those are 2 more points. This one over here, maybe just to get an idea, it's up here in quadrant 1, and this one over here, over 1, down 3, so that's actually quadrant 4. Okay, now that I have an idea of what this looks like a bit, I know I have a circle, I know where the center is, it's over 1, maybe I put a little note of it, that was my green one, yeah. So it's 1, negative 1 is my center, and the radius is 2. And my parabola right over here is going to have a vertex at -3, -1. And it's going to be a positive y squared, so it's opening in that direction too. Okay, 1, -1, and the radius is 2. Those are 4 points on my circle, and best as I can, trying to keep it as round as possible. Sometimes it turns into a bit of a diamond. Ooh, there, got a little lumpy. There's my circle, and I know my parabola is going to end up passing through these 2 points because they definitely intersect on the y-axis, which I saw before. We also found that our parabola is going to have a vertex at -3, -1, -3, -1 right there, and my axis of symmetry is y equals -1. It's horizontal instead of vertical like the ones we saw in dealing with functions in Algebra 2. Also, because I have a 1 in front, I mentioned this a value right over there. Because I have a 1 technically in front there, that means I sort of have that parent function shape. And what was that parent function shape running sideways? It's going to be over 1, up 1, but now it's sideways, 1 and 1. Then I go 1 and 3, out 1 and 3 this way. Well, that worked out nicely because those are the other points I found. Out 1 and 3. So these intercepts are just a little shy of being in line with those 2 points. Over 1, and we'll get 5 out of this one, and 5 out of that one. So far, so good. So I have that right there. See it cutting through like I predicted earlier. And here again. Oh, sorry. Holding the pen funny so I could kind of see, but oh boy, a little sloppy. Okay, so that's my parabola right there. Now these points where they intersect, just gonna label them a little bit better. That point right there is the point 1, 1. This point right over here, over 1, down 3. That other point of intersection right over here, that's going to be 0, -1 minus the square root of 3. If you think about it, it makes sense that it's coming off of -1 the same amount each way. -1 plus something and -1 minus something. So it makes sense because -1 is your axis of symmetry right there, your horizontal axis of symmetry. And then that one is 0, I'm going to make my ones like that, -1 plus square root 3. Writing it as an irrational number is just way more accurate than writing it as a decimal.